Part A wants us to discuss whether this mythical student is right that we can distinguish these three isomers using carbon-13 NMR. Now remember that chemistry is a nuanced subject. You don't necessarily have to just say yes he's right or no he's wrong. The answer could be well kind of up to a point, and we'll see that that's actually the case. Now carbon-13 NMR is very different from proton. So remember, you don't have splittings, all that complication. You only have two things that are important in carbon-13 NMR, which are the chemical shifts, and those are obviously going to be very similar because you've got the same functional groups, so there's really nothing to say about those. But the other thing that's important is the number of peaks, and that would be the way that potentially we could distinguish these. So the key thing to notice is that this one, which is the 4-nitro isomer, is symmetrical. So it has symmetry down the middle there, and that means that that carbon and that carbon are equivalent, because if you just flip the ring over they would swap places and you still have the same thing. Likewise, that carbon and that carbon are equivalent. Okay, so you will only have one peak each from those two, and then you'll have one from that carbon and one from that carbon. They'll all be those. You don't really need to say what their chemical shifts would be, but if you want to say that, you can do it. And of course they'll all be aromatic, because although this carbon is also bonded to an oxygen, remember, whichever environment predicts the bigger shift, that's the shift you go with. And since the aromatic shift is bigger than the CO shift, the fact that it's bonded to an oxygen is neither here nor there. The same goes for the carbon-nitrogen here. So all 6 of those hydrogens are in a aromatic environment. So within that part of the spectrum, 110 to 160 ppm or so, you will have not 6 but only 4 peaks. One from that one from those two, one from those two, and one from that one. So that will have 4 peaks. Now these other two have no symmetry, okay, because OH is different from NO2, so there's no way you can draw a line of symmetry through that one, or indeed through this one. And that means that all 6 of the carbons will be different. So again, they'll all be in that aromatic region, 110 to 160 ppm, but these ones there'll be 6 of, and the same for this. So you need to write these numbers down. Don't just say vague things like they'll have different numbers of peaks. They need to know how many. So 6 peaks for this, 6 peaks for this, so those two can't be distinguished. They wouldn't have identical spectra, but you wouldn't know which one was which. You know, they'd have slightly different shifts, but you wouldn't know which one was which. So you have to say those two you can't distinguish, but this one you can, because it has only 4 peaks. So C13, remember, it's very simple to interpret at our level, because the only things you think about are the chemical shifts and the number of peaks, and that was the key here. Part 2 is one of those questions where you have got to be really kicking yourself if you didn't get full marks for this, because it's one of those explanations that we tell you to memorise, that you just have to know, because if you try and make it up you get it wrong. So you just learn it in advance, and then when it comes up in the exam it's a joy, because they're easy marks. You can shut down your brain for a minute and just trot it out and not have to think about it. So why does phenol nitrate more easily than benzene? The lone pair, or a lone pair, on the oxygen in phenol is delocalized into the pi electron system of the ring. Now that word delocalized is important. You really need that there. And if you use other words like dissociated, people sometimes say, but that's just not, doesn't mean the same thing. So make sure you learn the proper words, and it's got to be a lone pair, not a spare pair or a free pair. Even an unbonded pair they probably wouldn't accept. You've got to use the proper terminology. So a lone pair in phenol is delocalized into the pi electron system of the ring, so that gets you 1 mark. And then you say this increases the electron density in the ring. And again, electron density is really the only term that they will accept there. it's definitely not electronegativity, which means something else altogether. And if you say number of electrons, well, that's closer to the right idea, but it's not a sort of whole number. It's just the idea that you're kind of borrowing, if you like, a share of the electrons from the oxygen. So number of electrons is kind of misleading. So electron density is what you have to say. That gets you the second mark. And this makes it, or makes the ring, more attractive to electrophiles. That word attractive is important, because they want the idea that it's actually drawing in the positively charged or delta positively charged electrophile. So don't just say it's more reactive or reacts more easily. They want that idea of attraction. So more attractive to electrophiles, which means that it's more reactive. And that's all you need for the 3 marks. Okay, so if you've prepared that in advance, that's dead easy. Otherwise, very unlikely to get the right wording. Part B wants us to complete this sulfonation mechanism for methylbenzene. And the point is, this is not a reaction you're meant to know about in advance, but it tells you this is an electrophile. So you think, oh yeah, it's basically going to be the same as the ones you do know about. And you know 3 electrophilic substitution mechanisms, because you know nitration, you know halogenation, and you know Friedel-Crafts. And so if you think about any one of those, so let's think about halogenation, for example, where you might have something like Br plus here as your electrophile. And of course you've learned that the curly arrow goes like that. So a pair of electrons comes out from the delocalized pi system and is used to form a new bond to Br+. And that's the step that kickstarts the mechanism. So you're going to think, well, this is going to be the same. And they've helpfully put on already for you the dipoles here, so you know that it's that delta positive sulfur that's going to attract the electron pair. So you just do the identical thing. Okay, make sure you draw the curly arrow accurately. It's got to come from the circle in the middle to show that it's a pair of electrons coming out from the delocalized pi system, and it's got to point directly at the sulfur to show that that's the atom that you're making the bond to. Now the complication is that if a pair of electrons coming into that sulfur, it's actually going to kick one of the other pairs out, because it's not a positively charged one, it's only delta positive. And in that case, you know, it's like in nucleophilic substitutions and so on, where an incoming pair of electrons boots out one of the other ones. So at the same time, you're going to get that happening. Now you might not have guessed immediately that that would happen, but if you look at the product, you can see it has happened. That what was a double bond here has broken to become single bond O-, and that should prompt you to think, oh yeah, I've got to have an arrow like that to give me the O-. So based on that, you should now be able to draw your intermediate. So you're still going to have this, and you're now going to have a bond to the sulfur, because that's what that curly arrow shows, and you're going to have these 2 oxygens unaffected, but this double bond has become a single bond O-, with a new lone pair there, because what used to be the bonded pair there has become the lone pair on there. Now the question is, what's going on in the middle there? So again, if you can't instantly remember, or you can't instantly sort of figure it out, then think about what happens in the bromination mechanism, which you have memorized. And if you haven't, then you absolutely need to, which, remember, goes like this. So the new bond is made to the bromine while the hydrogen is still attached there, and so you get this intermediate with the partially delocalized system in the middle there. And then the way that goes through to product is that the bond to hydrogen breaks, and that pair of electrons goes back in to reform the full delocalized pi system. So this is going to be exactly the same. Okay, so you draw your delocalized system going just around those 5 carbons, but not the 6th one. You draw the hydrogen still attached here, and you draw the positive charge there. So it's exactly analogous to what was going on here. And the movement of an electron pair which gets you from here to there, again, is exactly the same as it was there. That you have a curly arrow going from the bond, showing that that bonded pair is now going to go back into the ring to become part of the delocalized system again. And so that's the structure of the intermediate that you needed.